So here, as you can see, there is this encoder-decoder architecture, but you need to understand that the encoder-decoder architecture is in addition to the encoder-decoder architecture, which is mapping input x1 to xt to y1 to yt. We are also having another intermediate function called alpha t1, alpha t2, etc., which is basically a weighted function which says that what is the relative attention I should give for generating yt at st to each of the input x1, x2 to x capital T. So we have alpha t1 till alpha small t capital T, which is basically altogether should be 1, as you can imagine. But suppose I have more attention to, say, the first word and second word, then it may be that alpha t1 is 0.5, alpha t2 is 0.4, and remaining all together add up to 0.1. So y small t will be derived by a more stress on first two words as compared to other words. So here what we are deciphering is the attention function, which is the alpha t1 to alpha t capital T, in addition to decoding the encoder-decoder function, which is the h vector. So what you do here is each output word yt depends on a weighted combination of all the input states, not just the last input state. So this is a very important digression from the conventional encoder-decoder, architecture. So alphas are weights that are defining how much of each input state should be considered in terms of weighing to derive the y small t. So for example, if alpha 32 is a large number, that means that the decoder is paying a lot of attention to the second state in the source sentence while producing the third word of the target sentence. So no wonder we also want to make sure that alpha summed over all the numbers, alpha t1 to alpha t capital T should be 1. Same way alpha t minus 1, 1 to alpha t minus 1 capital T should be 1. So now you can see how you are going to model the function as not just the intermediate vector, but also the corresponding attention model, which you need to capture. So such kind of model is called as encoder-decoder models with attention. And these are quite powerful in real applications, especially in really generic chatbots, open-ended chatbots, very generalized machine translation, etc., where attention is an inherent characteristic of languages. So here, for example, if you see the translation from, let's say, the French to the target English, and you can easily see that the output, say you look at the word called destruction, it is looking at two different words in the original sentence, la destruction. Similarly, if you say Syria, it is looking at la Syrie. So it is important to understand that we have to, the translation is not 1:1, but many:1, where you are translating the weights of influence of many:1 models, which is what we call as the attention model, which we need to derive in addition to the original model. So I hope you got the gist of the attention model as a disruptive addition to the conventional encoder-decoder model. There are several extensions to these recurrent neural network models, like end-to-end memory networks, neural Turing machine, but these are beyond the scope because these are all quite in lab. As we speak, we are still not seeing much practical upsides yet. But attention models definitely have caught on the attention of the community and are giving rise to huge number of applications as we speak. And in fact, if you look at the combination of the concepts you've gone through till now in the RNN space, you're looking at first backpropagation through time, then RNN concept itself by a loop in networks, then concept of vanishing gradients, then handling that with an LSTM architecture or a GRU, then advanced architecture like bidirectional LSTM. Then we're looking at advancement of that to encoder decoder architecture, and then finally adding the notion of attention to the encoder decoder architectures. It's not that attention models is applicable only to encoder decoder. It could be more generic. As we are speaking, there's a lot of work happening in the industry and research community on attention models. And as we speak, we will see lot more applications coming and using such models for real life practical applications. So, having covered the concepts, what we will do is we will look at two sample applications. One, a plain encoder decoder architecture on a toy application where we're trying to simulate a simple mathematical operation and trying to learn the function of mathematics by creating a mapping function between input sequence and output. Then we will look at one example of attention model in neural machine translation, where we look at giving an input sentence from a corpus and seeing how we can create a translation model using the encoder model, decoder model with attention.